Hello students, the purpose of this video is to get you acquainted with complex numbers. So in this course we have been talking about real numbers so far. Any number that you can think of was considered a real number, but there are actually some numbers that are outside of the system and they are called complex numbers, and that's what we're talking about today. So I want to introduce you to something called the imaginary number, and we represent this with the letter I, and you want to know that I is equal to the square root of -1. So up until this course, you probably were told by some math instructor that you had before that you couldn't take the square root or the radical of a negative value, and that's true if you want your solution to be a real number. But if it is okay for you to have complex number solutions, then you actually can take the radical of a negative value. So anytime you have a negative, it is going to create an I outside of your radical symbol. And then this is a given based off of knowing that I is equal to the square root of -1. If I were to square both sides, it would get rid of my radical and leave me with just -1, and then I would have I squared. It's important to keep that in mind because there are times you may be solving and you end up with the value I squared, and anytime you have that, you want to go ahead and replace it with -1 since we know that that is its equivalent value. So I put a few cute little jokes here to just get in tune with my math joking side. So if you want to go ahead and pause this video and read over these, they're really cute and they give you a good little giggle. So I have a slide here that shows some relationships between I squared, I to the fourth, and I to the fifth. And the idea is I want you to understand that whenever you raise I to a particular exponent value, you'll always get either positive or -1 or positive or negative I. And so it's kind of cool. If you just look at these relationships, you'll notice that when you go to simplify, you'll always have those similar values. Certainly not something that you need to memorize. I'm not concerned about you memorizing this, but just something to notice regarding the relationships of multiplying imaginary numbers to itself. So I've given you an example here. I've actually given you three, and I've given you their respective solutions, but I want to make sure you feel confident on how to simplify these. So if I look at letter A, I have the square root of -25, and you'll notice that negative, if I take the square root of a negative, it produces I, and so I've done that in pink. I've taken the I to the outside. And then I have the square root of 25, which I know equals 5, and so I end up with a final solution of 5I. If I look at the negative square root of 12, again, if I take the square root of a negative, that produces the I, which ends up being on the outside. And then if I'm going to take the square root of 12, I have to think about how to simplify radicals. Two numbers that multiply to 12 are 3 and 4, and two numbers that multiply to 4 are 2 and 2. I need a group of 2, and then I leave whatever is left over, and so that's how I end up with my respective two square roots of 3. Okay. And then square root of -13, unfortunately, 13 itself doesn't break down, so my final answer still has the square root of 13, but I am able to break down the negative and take out the I to the outside. When I think about complex numbers, sometimes I may want to write them in standard form. If I'm ever writing a complex number in standard form, it's going to be in the form A plus BI. A is the real part of the solution, and the BI is the imaginary part. If you look at what we were working with a second ago, so in letter A, I have 5I. If I wanted to write that in standard form, there is no real part, so I would say 0 plus 5I. If I was looking at letter B, I would have 0 plus 2I square roots of 3. If I was looking at letter C, I would have 0 plus I square roots of 13. So again, these are each of the solutions written in standard form, where I'm considering a real part and an imaginary part. If I don't have an imaginary part, that would be 0, and so then I would have a real number solution. Now, when completing binary operations with complex numbers, you're going to add like terms. So things that have I, they'll get combined. Things without I, meaning the real number solution parts, I will add those parts together. And then with subtraction, you just want to remember that you need to distribute your negative sign. So I encourage you to pause this video before I provide the solution and try to combine these like terms. So as I go to work out the solution, I notice I have a minus sign, so I'm going to want to start out by distributing that. And I have negative 2 minus 4i plus 5 plus 2i, and then a minus 3 and a plus 6i. And so I'm going to begin by adding my real parts, which are negative 2, positive 5, and a minus 3, and that actually ends up getting me 0. And then I'm going to go ahead and add my minus 4i, plus 2i, plus 6i, which gets me 8 minus 4, so positive 4i. And that is my final answer in standard form. Looking at my second problem, I have 8 minus 3i. I need to distribute this negative, so minus 2i minus 4i. I am going to combine my like terms, so 8 minus 2 plus 5 is 11. And then I have negative 3i minus 4i plus 7i, which is plus 0i. Okay? And again, that is written in standard form. So in number 1, I only have a complex portion. In number 2, I only have a real portion. Multiplying complex numbers works the same way. So in letter A and B, I've provided you in both cases with binomials. So we are going to FOIL these just as we would any other binomial. So looking at letter A, I have 3 plus 4i squared. So that means I'm going to multiply 3 plus 4i by itself. First gives me 9. Outer gives me 12i. Inner gives me 12i, and last gives me 16i squared. And I'm going to go ahead and combine like terms, so 12i and 12i, those are like, so that gives me 24i. I'm going to bring down my 9, and then I want to do something here because I notice that I have I squared, and I know that that is equivalent to negative 1. So I have this 16 times this negative 1, which gets me 9 plus 24i minus 16. And I can go ahead and combine my like terms that I have here. And that's going to give me negative 7 plus 24i. And that would be my real number solution. Well, excuse me, my real number solution and complex value. So that would be my solution in standard form. Okay, if I look at letter B and I FOIL, I have 5 times 5, which is 25. My outer gives me negative 10i. My inner gives me positive 10i. And my last gives me negative 4i squared. And interesting, if you notice here, I've given you conjugates. So you know that means that your outer and inner terms should be exact opposites of one another so that they cancel out. And sure enough, they do. These do cancel one another out. So I'm going to go ahead and cross this out. I also notice that I have an I squared, which is equivalent to negative 1, and that's being multiplied by negative 4, and then I have the 25, and so now I have 25 plus 4, which gives me a final solution of 29. So it's really cool with our conjugate values. We lose our I because we'll always have the I squared that we can plug in our negative 1 value for, and we end up with a real number solution. And if you want to see the steps written out for you again, feel free to pause this video. So again, with conjugates, just as we saw before, if I give you one binomial, you can create its conjugate. It's going to be the same values, but the opposite sign. And as we saw in our last example, a similar thing is going to happen whenever I have complex conjugates. When I do my FOIL process, so 4 times 4 is 16, my outer gets me 8i, my inner gets me 8i, and my last gets me negative 4i squared. With complex conjugates, I'm always going to notice that my like terms for my outer and my inner are going to cancel out, and my term that contains the I is going to be able to be replaced with its respective value, in this case negative 1, which is going to allow me to simplify this process in order to get a real number solution. So super, super nice when we're working with complex conjugates. Now, when I divide complex divide complex numbers, the rules are going to be the same, just as any other division that we've had. You'll notice that I have binomials, so I can't separate parts on top and bottom. They have to look exactly the same. So if I had, 3 plus 2i over 3 plus 2i, I could simplify these because they look exactly the same on top and bottom. So they must be exactly the same. Okay. Now, when I am working with complex numbers, similar to the rules of radicals, we don't want imaginary values in our denominator, so we want to go ahead and get rid of those, and that's why we discussed the concept of complex conjugates. So if I multiply the denominator by its conjugate, as you see I've done here in blue, and if I do it to the bottom, I have to do it to the top, I am able to get rid of I in my denominator. So I'm going to go ahead and work this out for you. So let's do purple. So I'm going to multiply by the conjugate, 3 plus 5i, in top and in bottom. And in the numerator, that gets me 24 plus 40i plus 6i plus 10i squared. And in the denominator, that gets me 9 plus 15i minus 15i minus 25i squared. If I want to go ahead and simplify, that's 24 plus 40i plus 6i is 46i. And keep in mind that I squared is equal to negative 1. So 10 times negative 1 is negative 10. In the denominator, 15i minus 15i cancel out. Keep in mind that I squared is equal to negative 1, and negative 25 and negative 1 is equal to a positive 25. And then I have that 9 in the front. If I continue to simplify, I end up with 34 in my denominator, and 24 minus 10 is 14 plus 46i. This is one way that you can write your answer. Of course, we know that we can always simplify. So here's where we were. We can actually simplify. These fractions do all go into one another. So you could end with your final simplified value of 7 over 17 plus 23 over 17i. Again, this is also the same thing as 7 plus 23i all over 17. So any of these ways that you want to write this are all equivalent. This is just a review slide just to make sure that you're remembering how to solve quadratic equations. You're welcome to work through these problems and make sure you feel confident on these. I'm not going to solve them for the purpose of this video because I'm really just trying to make sure you feel good with complex numbers. But if you want to go ahead and pause and jot this problem down, I'll give you a second to do that. I have also provided you with the solution to how to solve that quadratic. Notice that I did the process of extracting the square root. I also want to make sure that you're thinking back on how to solve quadratics that may contain fractions. Remember that you're welcome to get rid of your fractions, so I encourage you to pause this video and try to solve. And I have also provided you with the solution. I started by eliminating my fractions first, and then I performed the quadratic formula. As always, I hope that you found this video helpful. If there's anything that I can do or to assist you with, please do not hesitate to let me know. And I hope you all have a wonderful rest of your day.